Welcome back. This is the last lesson, 9E, in which we will do equilibrium constant calculations. Example 8 is on page 168, and it's the third example on that page. So they say that carbon monoxide and hydrogen reacts as follows. So we have carbon monoxide, a gas, reacting with 3 hydrogen molecules to form an equilibrium situation with methane, a gas, and water, also in the gaseous phase. Now, to solve the problem, I know that I have to write the mole ratio to help me with calculations. So 1 mole carbon monoxide will react with 3 moles hydrogen to give 1 mole of methane and 1 mole of water. When 1 mole of carbon monoxide reacts with 3 moles of hydrogen in a 10 cubic decimeter container. So somewhere I need to write that the volume of the container is 10 cubic decimeters. And the temperature is 927 degrees Celsius. The reaction reaches equilibrium with 0.4 moles of water in the equilibrium mixture. Calculate the molar composition of the equilibrium mixture and the Kc value. So they want us to calculate the moles of each of the substances at equilibrium, and then from there the Kc value. So at the start we started with 1 mole carbon monoxide and 3 mole hydrogen. We started with 0 mole methane and 0 mole hydrogen. They say the reaction reaches equilibrium with 0.4 mole of water. So I don't know what was used or formed at this point in time, but at equilibrium we end up with 0.4 mole of water. So if 0.4 moles of water was at equilibrium, it means that 0.4 moles of water must have been formed. Now the ratio between the moles of of methane and water is 1 to 1. That means that 0.4 mole of methane must have been formed. And because the ratio between the mole of carbon monoxide and the mole of methane is 1 to 1, it means that 0.4 mole of carbon monoxide was used. So what I normally do is I put a little negative there to show that it was used, and I put little positives here to show that myself that it was formed. Now the ratio between the carbon monoxide and the hydrogen is 3 moles to 1 mole. 3 moles hydrogen to 1 mole carbon monoxide. That implies that I need to take the 0.4 and multiply it by 3 to get to the moles of hydrogen that was used. And I'm going to put a little negative Now 4 times 3 is 12, so it's 1.2 mole of the hydrogen was used. From there we can go to 0.4 moles of water was formed, 0.4 moles of methane was formed. To get the amount of hydrogen left at equilibrium, it's 3 minus 1.2, so that is 1.8 mole. And then 1 minus 0.4 is 0.6 mole of carbon monoxide. To get the concentrations at equilibrium, I'll have to divide by 10, the 10 cubic decimeters, the volume of the container. So that gives me 0.06 mole per cubic decimeter, 0.18 mole per cubic decimeter, 0.04 mole per cubic decimeter, and 0.04 mole per cubic decimeter. Now it's easy to get the Kc value. It would be the concentration of the methane times the concentration of the water divided by the concentration of the carbon monoxide times the cube of the concentration of hydrogen. So it's 0.04 times 0.04 divided by 0.06 times 0.18 to the power 3. And that brings us to an answer of 0.04 squared divided by open brackets 0.06 times 0.18 cubed close bracket, and I get 4.57 is the ratio called the Kc. This brings us to the end of the calculations. Thank you for watching.